Hello friends, this is the fourth session in haloalkanes part. Till now we have studied the introduction, their classification, nomenclature and methods of preparation of haloalkanes. In this session we shall deal with their physical properties and learn some of their chemical properties also. So the first one is physical properties. Physical properties of haloalkanes. You have been studying about physical properties since your first year in alkanes, alkenes, alkynes, then benzene and its compounds, etc. The very first physical property always is their physical state. In haloalkanes, the first two members are gases. Those containing two carbon atoms, they are gases. Next, up to 18, they are liquids, and higher members are solids. So how many are gases? The first two members are gases, up to 18 members are liquids, and higher members are solids. When it comes to their color, when it comes to the color of haloalkanes, the chloroalkanes are usually colorless. They are usually colorless, but bromides and iodides, they develop color only when they are exposed to light. Unless they are exposed to light, they too remain colorless only, but if they are exposed to light, they will become colored. So all haloalkanes are colorless. Chlorides are always colorless. Bromides and iodides will develop color only when they are exposed to light. If you want to know about their odor, then all haloalkanes are usually odorless, but the lower members are having sweet, pleasant odor. All haloalkanes are odorless, lower members are having only sweet, pleasant odor. This was first property. The second property is their boiling point. Sir, why do we study generally about boiling point? Is because the first two members are gases, we generally do not consider them. After 18 carbon atoms, whichever member comes, they are solids. Rest of all of the members are liquids, so boiling point becomes a major property of them. So the boiling point of haloalkanes is in the order alkyl iodides have higher boiling point than alkyl bromides, than alkyl chlorides, than alkyl fluorides. Why this trend? It is because, see, in periodic table down the group, fluorine comes first, then comes chlorine, then bromine, then iodine. So down the group, atomic number increases, atomic mass increases, so atomic size also increases. As a result, when atomic size increases, the van der Waals forces between them also increases, isn't it? So as a result, their boiling point is in the sequence. Alkyl iodides is having higher boiling point than bromides, than chlorides, than fluorides. If you compare their boiling points with normal hydrocarbons, any alkane with a haloalkane, because they are polar, because they have dipole-dipole interactions, because they have van der Waals force of attraction, therefore the boiling point of haloalkanes will be more than corresponding hydrocarbons. The third property is density. Often density and boiling point go hand in hand. It means as boiling point increases, density also increases. But you should remember that when number of carbon atoms increases, density also increases. If number of halogen atoms increases, density also increases. If atomic number of halogen increases, density also increases. If atomic mass of halogen increases, then density also increases. So who has higher density? Alkyl iodide, the same trend, alkyl iodide, then alkyl bromide, then alkyl chloride, then alkyl fluoride. It is because of higher van der Waals forces, greater dipole nature and more polarity. You should remember that if number of carbon atoms is increasing, density increases. If the number of halogen atoms are increasing, density increases. If the atomic number of halogen is increasing, density increases. If the atomic mass of halogen increases, then also density increases. The only point to be remembered is if branching increases, boiling point decreases. Boiling point remains higher and higher only when there are straight chains. If anywhere branching appears, then boiling point decreases. Understood? Boiling point decreases only when branching increases. The fourth property, it is solubility. Solubility of haloalkanes. You should be aware that any compound which is polar will be soluble in a polar solvent, like dissolves like. It follows this principle. So on that note, we say haloalkanes are polar. They are polar. If they are polar, then they should be soluble in water. They should be soluble in water. But even though haloalkanes are polar, they are not soluble in water. They are insoluble in water. Why are they insoluble in water? It is because haloalkanes cannot break this hydrogen bond of water. Haloalkanes fail to break the hydrogen bond of water. Also, they fail to make a new bond with water. For this reason, haloalkanes are insoluble in water. You might expect this as a 1 mark question in your theory exams. The question will be, even though haloalkanes are polar, why are they insoluble in water? The only reason is they failed to break the hydrogen bonds existing in water molecules, and they also failed to make new hydrogen bonds with water molecules. For these two reasons, haloalkanes, though they are polar, they remain insoluble, or they are always non-soluble in water. The last property is their flammable nature. Haloalkanes are highly non-flammable, or you can say they are less inflammable than corresponding hydrocarbons. We know that hydrocarbons are flammable, so they are used as fuels. But haloalkanes, they are less inflammable when compared to their corresponding hydrocarbons. For this reason, there is a very popular haloalkane, that is carbon tetrachloride, which is available in the market in the name pyrene. This is used as a fire extinguisher. What is a fire extinguisher? We all know. It douses the fire. So, haloalkanes are less inflammable when compared to their corresponding hydrocarbons. For this reason, they are used as fire extinguishers. One popular example is carbon tetrachloride. This becomes the 5 physical properties of haloalkanes. Now let us see their chemical properties. Chemical properties of haloalkanes. Haloalkanes show several chemical properties. They are divided into 3 headings. The first heading is their reaction with metals. The second is elimination reactions. And the third is nucleophilic substitution reactions. Haloalkanes show these 3 types of chemical reactions. The first one is reaction with metals, second is elimination reactions, the third one is nucleophilic substitution reactions. Whenever these two are dealt with, we shall explain them in detail. Now let us see only the first one, reaction with metals. Under reaction with metals, we have the first one is reaction with magnesium. Reaction with magnesium. A very popular reaction. whenever any haloalkane reacts with magnesium powder, you get alkyl magnesium halide. A very easy reaction, but one condition is that you are supposed to write dry ether. What is this reaction? When any alkyl halide reacts with magnesium powder in the presence of dry ether as a solvent, you will get alkyl magnesium halide. You get alkyl magnesium halide. These alkyl magnesium halides were prepared for the first time by a scientist called Grignard. Therefore, the product is commonly called Grignard reagent. It is called Grignard reagent. So, what are alkyl magnesium halides commonly called as? They are called as Grignard reagents. How is a Grignard reagent prepared? A Grignard reagent is prepared by reacting alkyl halide with magnesium in the presence of dry ether. What do we get? We get alkyl magnesium halide. What are they commonly known as? They are known as Grignard reagents. What is their general formula? RMgX. One common example could be CH3Br plus Mg, methyl bromide plus magnesium in the presence of dry ether will give you methyl magnesium bromide. What is it called? Grignard reagent. You should also remember what is the role of dry ether in this reaction. Then remember, Grignard reagents are highly ionic compounds. Generally, how do we represent charges? Carbon gets partial positive, halogen gets partial negative, isn't it? Whereas in Grignard reagents, the metal carries positive charge, whereas the surrounding alkyl group carries negative and the halogen also carries negative charge. Because they are highly ionic compounds. Who are highly ionic compounds? Grignard reagents are highly ionic compounds. For that reason, they react with any source of proton available. For example, if during the preparation of Grignard reagent, if anywhere water was present, if anywhere water is present, then it reacts with any source of proton, like it can be split as HOH. It will react with any source of proton and it will become RH. Then hydroxy magnesium halide. What is this? It gives rise to the formation of an alkane. It will never form a Grignard reagent, but it will become an alkane. For this reason, during the preparation of Grignard reagents, you should keep the medium dry and inert. To keep the medium dry and inert, what do we use? We use a dry solvent such as dry ether. A dry ether is the solvent which does not contain, which does not generate protons to react with alkyl halides. So, what all should you remember during the preparation of Grignard reagent? You should remember the reactants. They are alkyl halide, then alkyl halide and magnesium powder. The solvent should be dry ether. Compulsorily, you are supposed to write dry ether. You will get alkyl magnesium halide and they are called Grignard reagents. Their general formula is RMgX. Understood? Then during the preparation of Grignard reagent, you are supposed to use dry ether compulsorily because Grignard reagents are highly ionic compounds. They react with any source of proton available to convert themselves into alkanes and they will no longer remain as Grignard reagents. To avoid this reaction, you are supposed to use inert solvent like dry ether. This is reaction with magnesium. Then the second reaction is reaction with sodium metal. A very popular reaction since your first year days. When any alkyl halide reacts with metallic sodium, same in the presence of dry ether, you will get alkanes. You will get alkanes. How do you balance this? Since there are 2R, write 2 here. Then there are 2X, so write 2 here. Then write 2 metallic sodium. Everything is balanced. So when any alkyl halide or haloalkane is reacted with metallic sodium in the presence of dry ether, you get higher alkanes. You get higher alkanes. This reaction is called Wurtz reaction. It is called Wurtz reaction. Always remember, named reactions are important from exam point of view. All named reactions or all named reagents, named reagent reactions or named reactions, they are important for exam. So Grignard reagent formation is an important question. Woods reaction is a hot favorite question. So how is Woods reaction done? It is done by reacting an alkyl halide or a haloalkane with sodium metal or metallic sodium in the presence of dry ether, which will give you higher alkanes. One example, in place of R you write CH3 Cl plus Na. If this method is not feasible, you can try the other also. You can split the haloalkane into two, means you take two molecules separately. Then how do you write them? You write it in this fashion, Cl dash CH3, both are same, no? So write 2 here, separate this much part, you will get CH3 dash CH3 plus 2 NaCl. This is best example for Woods reaction. So there are only 2 reactions of metals for your syllabus. One is with magnesium, the other is with sodium. With magnesium it forms the Grignard reagents, with sodium metal it forms alkanes. With magnesium, if it forms alkyl magnesium halides, it is Grignard reagent. If it forms alkanes with sodium metal, then it is called Woods reaction. This was your first chemical property, reaction with metals. Let us see the second one. It is elimination reactions. Very interesting reaction is second one, elimination reactions. Elimination means to remove, to eliminate. Elimination, removing some part from a given compound. Here our given compound should be a haloalkane. So to remove, what part should be removed easily? What part can be removed easily? It is halogen part. So elimination reactions are otherwise called as beta elimination also. Why are they called beta elimination? I will tell you after some time. They are also called beta elimination reactions. Okay. For this reaction you need alcoholic KOH. So for this you take any haloalkane, for example RCH2 CH2X. You take this haloalkane, react it with alcoholic KOH and heat. Then now remember these steps. While you are carrying out elimination reaction, you are supposed to write alcoholic compulsorily. If this alcoholic is not written, we assume it as aqueous. In presence of aqueous, it takes place a substitution reaction and not elimination. So if you want a haloalkane to undergo elimination, you are supposed to use compulsorily alcoholic KOH. Without indicating anything here, it gives an indication that it is aqueous. So what should you write? You are compulsorily going to write alcoholic KOH. Heating is also done. Heating is also compulsory. Without heat, this reaction will not proceed. So what happens now? You go on eliminating. You should eliminate some part from haloalkane. So you eliminate this part, K and X. This is one part, KX is gone. Then from whichever carbon you are removing halogen, leave that carbon. From the adjacent carbon, eliminate one hydrogen. So you eliminate one hydrogen along with this OH. So you will end up with H2O. Fine. What else is remaining? R dash CH, because hydrogen is lost. This bond will become double bond CH2. It will become CH2. What is this product? It is an alkene. It is an alkene. So the main product formed in elimination reaction is an alkene. Because you are removing hydrogen as well as halogen, both are removed, this reaction is also called as dehydrohalogenation. It is also called dehydrohalogenation. halogenation reaction. Means you are removing hydrogen as well as halogen. So it is called dehydrohalogenation. Now why is it called beta elimination? We number any haloalkane based on the position of halogen. Whichever carbon contains halogen, that should be given least number. So on that basis, this is 1, this is 2. If there were other carbons, they would have got number 3, 4, 5 and etc. Other than these, in common naming system, whichever carbon has halogen, that carbon is labeled as alpha. The adjacent carbon is beta, the next carbon is gamma and so on. Since you are removing hydrogen from beta carbon, therefore it is called beta elimination reaction. Elimination generally we define with respect to hydrogen. So in this case you are removing hydrogen from beta carbon, therefore it is called beta elimination reaction. You are removing hydrogen and halogen, therefore it is called dehydrohalogenation. For this reaction you need compulsorily alcoholic KOH. If alcoholic is not written, if it is aqueous KOH, then the formed product will not be an alkene, it will be an alcohol. Okay. So this reaction is elimination reaction. Let us see some examples and understand how exactly elimination should be done. If this is CH3, CH2, Cl, if it is ethyl chloride and it is subjected to dehydrohalogenation, then you will eliminate K and Cl. KCl is gone. Then from this carbon you have eliminated chlorine. Leave this carbon, go to the adjacent carbon, remove one hydrogen from here. That one hydrogen, this OH, it will give you H2O. What else is remaining here? CH, one hydrogen is lost, so 2 hydrogen, double bond, 2 hydrogen. You will get ethene. If the reaction is this one, CH3, CH2, CH2, Cl plus KOH, how? Alcoholic. Then what should be the product? Same, KCl is gone, water is gone. How water is gone? This OH and H from here. So the product will be CH3, single bond CH, double bond CH2. It is propene. If the reactant is CH3, CH, CH3, this was propyl chloride, N-propyl chloride or 1-chloropropane. This is 2-chloropropane. It is 2-chloropropane. Okay. If this is reacted with alcoholic KOH, if it is heated with alcoholic KOH, then you will eliminate K and Cl. You will eliminate water now. How do you eliminate water? You can remove hydrogen from either this carbon or this carbon. Both are same. So eliminate water. You will again get CH3, CH, double bond CH2. You will again get propene only. You will again get propene. So whether it is N-propyl chloride or isopropyl chloride, the products remain same. Let us see some higher example and understand the significance of this reaction. If it is 2-chlorobutane, if this is heated with alcoholic KOH, what product are you likely to guess? Let me make a guess. You will eliminate KCl, K from here, Cl from here, that is for sure. Now you will eliminate water also. From where should you remove hydrogen in this example? You have two chances. One, either from this carbon or from this carbon. You eliminate from anywhere. Assume if you are removing hydrogen from here, then your product will be CH3, CH2, CH, double bond CH2. This could be one product. What is this product? But-1-ene. Or else the other product will be, you have second chance of eliminating hydrogen from here. If it is done from here, then the product will be CH3, CH, double bond CH dash CH3. It is butene, but-2-ene. Identify the major product. Both seem to be correct, but only one is more appropriate answer. Which one should be the more appropriate one? Simply guessing will not help. This is done according to a rule called this rule. How do you pronounce this name? This name is pronounced as Zev's rule, to be written as Zev's rule, but to be pronounced as Zev's rule. What does this rule say? This rule says that it says during the elimination of hydrogen halide, during the elimination of hydrogen halide from a haloalkane, during the elimination of hydrogen halide from a haloalkane, hydrogen must be removed from that carbon, hydrogen must be removed from that carbon which contains less number of hydrogen atoms. Hydrogen must be removed from that carbon which contains less number of hydrogen atoms. Now you have two possibilities. This was first, this was second. This carbon has 3 hydrogens, this carbon has 2 hydrogen atoms. So what does the rule says? It says that hydrogen should be removed from the carbon containing less number of hydrogen atoms. So you are supposed to remove from this carbon. Some of you might ask, sir, this carbon had only 1 hydrogen, why didn't you remove hydrogen from here? From whichever carbon you are removing halogen, leave that carbon as it is. Do not disturb its hydrogens. Go to its adjacent neighbor atoms, either this carbon or this carbon. In these two, search whichever carbon has got less number of hydrogen atoms, remove hydrogen from there. That will be your major product. Then, sir, this should be our major product. Yes, true, this is our major product. Whether this will not form, it will also form, but its quantity will be very less. So elimination reactions are very important from all competitive exams point of view and even in theory exams. It is done according to which rule? Zev's rule, which says that during the elimination of hydrogen halide from a haloalkane, hydrogen must be removed from a carbon containing less number of hydrogen atoms. This rule is interpreted in some other way also, which says when hydrogen halide is eliminated or removed from a haloalkane, that product is formed in excess, which is more alkylated, Sir, how do I identify whether it is more alkylated or not? You separate double bonded carbons and count the number of alkyl groups on either sides. One alkyl group, second alkyl group. So there are 2 alkyl groups in this product. In this product, you separate the double bonded carbons and count the alkyl groups. It is only 1 ethyl group. So it is only 1 alkyl group. Here there are 2 alkyl groups. So that product is formed in excess, which is more alkylated. Which is more alkylated? The second one. Whichever rule is easier, you can remember that. I'll quote the rule once again. Zev's rule says that during the elimination of hydrogen halide from a haloalkane, hydrogen must be removed from a carbon containing less number of hydrogen atoms. In other words, the rule says when hydrogen halide is eliminated from a haloalkane, that product is formed in excess, which is more alkylated or which contains more number of alkyl groups attached to the double bonded carbon atoms. Let us see one final example to understand if you are able to do this or not. Take CH3, CHBr, CH2, CH2, CH3. This is 2-bromopentane. If 2-bromopentane is heated with KOH, how should it be? It should be alcoholic. Minus KCl minus H2O. I will not write the byproducts again in the product side. So you have 2 possible chances of writing the products. One is you can remove hydrogen from here or from here. From this carbon you will compulsorily remove halogen. After that you can remove hydrogen from here or from here. I will remove from here first time. CH3, CH, double bond, CH, CH2, CH3. pent 2-ene plus. One more, if you are removing hydrogen from this carbon, you will end up with CH2 double bond CH, CH2, CH2, CH3. This is pent 1-ene. To understand which product is major or minor, you separate the double bonded carbon atoms, count the number of alkyl groups, 1, this side 1, 2 alkyl groups. So it is major. It is major because if you separate the alkyl groups in the second example, if you separate the double bonded carbons in the second example, there is only one propyl group. So it is minor. Understood? Okay. So what is Sedgwick's rule? Sedgwick's rule says that during the elimination of hydrogen halide from a haloalkane, hydrogen must be removed from the carbon containing less number of hydrogen atoms, or else when hydrogen halide is eliminated from haloalkane, that product is formed in excess which is more alkylated. The third set of reactions is nucleophilic substitution reactions. This nucleophilic substitution reactions is a lengthy part which cannot be done in this session. So for that I need one entire session. That part we shall see in the next class. As for now, today you have studied about the physical properties, chemical properties. Under chemical properties you have studied only two chemical properties. One is reaction with metals, the second is elimination reactions. In our next session we shall study about nucleophilic substitution reactions. Thank you.